Hello everyone. In this lecture, I shall discuss the multivariate calculus followed by the Jacobian and Hessian matrix. Now coming to the word multivariate means we have more than one variable, right? That means suppose you are given a function f of xy. Similarly, suppose you are given a function f of xyz, three variables. Here f of xy is two variables, okay? Similarly, we can extend it to 4, 5, 6 and in general n variables, right? And if we recall the single variable calculus, where we have a function of single variable, where y is fx, y is a dependent variable here, y is a dependent variable here, and x is a independent variable here, So we are finding dy by dx as the differential coefficient, and also we can call it f dash, is not it? So similarly, we'll extend the differentiation for the function of several variables, right? And it is followed by the Jacobian and Hessian matrix, and subsequently we will discuss the maxima, minima, Taylor's theorem and Maclaurin's theorem for function of two variables. Then we will learn the Lagrange multiplier, right, and so on. So before we have the detailed discussion of this topic, let me to introduce myself, Professor Dr. Sushant Kumar Paikray, currently working as a professor in the Department of Mathematics, Veer Surendra Sai University of Technology, Budla, Odisha. Okay, so without wasting much of our time, let us now come to the topic. Now coming to the function of two variables, f is f of xy. We can differentiate it partially. F of x means del f by del x, right? Where we treat y as a constant, is not it? Already you know this constants, and we can denote it by p, right? And similarly, if we differentiate with respect to y, it is del f by del y, where we have x is our constant, right? And these things are already known, and we denote it up by our q. Similarly, for the second order derivative, we have fxx. Fxx means we differentiate twice with respect to x, right? So now this is, we denote it by r. And similarly here fxy is here del square f by del x del y. First we differentiate with respect to x, then with respect to y, or vice versa. And similarly here fyy is here del square f by del y square, right? And we can denote it by s, and we can denote it by t, right? These are the standard notation p, q, r, s and t. Now coming to the Jacobian, suppose you are given u is a function of x and y, and v is a function of your x and y. Okay, suppose I want to find the Jacobian here, the Jacobian j, or Jacobian j uv, or in short I find the j here, and I can denote it del uv by del xy. Okay, and it is given by the determinant u is differentiate with respect to x, u is differentiate with respect to y, v is differentiate with respect to x partially, and v is differentiate with respect to y, and we find the determinant of this, and this will be my Jacobian. Now this Jacobian will play an important role while we integrate the multiple integrations, okay, where we want to change the variable of integration, then the Jacobian will play the important role. Similarly, suppose you have the function of three variables. Suppose you have u is a function of u, x, y and z, and v is a function of v is a function of v, x, y and z, right? And we want to find the Jacobian here, juv, right? And this Jacobian will be also here some w, because determinant has to be the square matrix. Okay, w is a function of w, x, y and z, and your Jacobian j u v w, okay, will be my ux, uy, uz, vx, vy, vz, wx, wy, and wz determinant, okay, and we denote it del u v w by del x y z, right? In general, if we extend it to the function of n variables, right? Suppose your u1, u2 and un are functions of n variables, x1, x2, so on up to xn, right? Number of variables has to be same here, okay? Then what will be your Jacobian here? Your Jacobian u1, u2 up to un. It will be here u1 is differentiated with respect to x1 and u2 is differentiated with respect to x2, so on, so on, so on. Un is partially differentiated with respect to xn. Similarly, here it is u1, you make it u1 in first row, you make it u1 throughout. Then u2 is differentiated with respect to your x1, u2 is differentiated with respect to x2, so on, so on, so on. u2 is differentiated with respect to xn. Likewise, here un is differentiated with respect to x1 partially, un is differentiated with respect to x2, so on, so on. Here un is differentiated with respect to xn partially, and you find the determinant, okay? You find the determinant. Likewise, we can write it, it is not this, in other notation I can write it del u1, u2 up to un divided by del x1, x2 up to your xn, okay? In short, this is my j, this Jacobian is given by this. In particular, suppose we are in polar coordinate, x is equal to r cos theta, x is a function of r and theta, and y is a function of r and theta, right? This is in polar coordinate, So here in general, here x is equal to means I am taking r cos theta and y is equal to my r sin theta, right? So here what will be the Jacobian here? This Jacobian j will be xr x theta, yr y theta determinant. So what is xr? You see the partial derivative of x with respect to r is cos theta, partial derivative of x with respect to theta is your minus r sin theta, right? Similarly, your partial derivative of y with respect to r is your sin theta, and partial derivative of y with respect to theta is your r cos theta determinant. If you evaluate the determinant, right, it is r cos square theta plus r sin square theta. So r taken common, cos square theta plus sin square theta, this is equal to r into 1 is your r, right? So this Jacobian here is your r, right? So here it can be written as j r theta jxy by del xy by del r theta, okay. Now if I interchange the variable here, so what is my r here? R is here x square plus y square root over, here theta will be here tan inverse y by x, isn't it? Tan inverse y by x, here sin theta by cos theta, y by x tan theta. So here theta is tan inverse y by x. Now here r is a function of x and y, r is a function of x and y, and theta is a function of x and y here. Now what will be the Jacobian in this case? This Jacobian will be del r theta by del xy. Suppose I denote it by j dash. Right? Then it will be your what? It will be your rx, ry, and here theta x, theta y. If you simplify it, it will give you here 1 by r. It will give you here 1 by r. So now how it is? So you see here r is this. What is my rx? So rx is 2x divided by 2 into root over of x square plus y square. Is not it? 2 cancel. So it is x by r. X is here r cos theta divided by r is here cos theta. Is not it? Similarly, you can find here ry will be sin theta, and similarly you can find here theta x, right? So theta x, derivative of tan inverse x is 1 by 1 plus y square by x square. By chain rule, derivative of y by x with respect to x is here minus y by x square. So this will be here minus y by x square plus y square. So y is here r sin theta minus r sin theta, and x square plus y square is here r square. So this is here minus of sin theta divided by r. So therefore the z dash in this case is, suppose my del r theta by del xy, right? Del xy. Then this will be my rx. So it is the determinant of rx is here cos theta, ry is here sin theta. Similarly, theta x is here minus sin theta by r. Likewise, you find theta y will be here cos theta by r. Okay. So now if you find the determinant, this into this minus this into this, so 1 by r cos square theta plus sin square theta is here 1 by r. Okay. So at this juncture I can tell you an important property. Property number 1. If here j is del uv by del xy and z dash is suppose del xy by del uv, right? Then here j multiplied with z dash, okay, will be here 1. As we see it here, it is 1 by r and this is here r. If you multiply them together, this will give you 1, right? Similarly, coming to property number 2. Property number 2. It is the chain rule of Jacobian. Chain rule of Jacobian. Suppose you have u is a function of uxy and v is a function of vxy. Again this x is a function of x r theta, and this y is a function of y r theta, right? Then what will be our Jacobian? Jacobian del uv, right? Del uv with respect to r and theta, del r theta, right? It will be, you see, we are moving to r and theta via x and via y. So this will be your del uv, right? U and v directly to x and y by del xy, and then x and y to r and theta del xy by del r theta, right? So accordingly, this will be your ux uy vx vy determinant, and this will be your xr x theta yr y theta. So the product of this matrix, okay, this product of this matrix. So now you find the product of this matrices, then you take the determinant. So in that way you multiply this, right? ux into xr plus uy into yr, and accordingly you multiply this with this, ux x theta plus uy and y theta. Again you multiply in this way, so this is vx xr plus vy yr. Then you multiply this, it is vx x theta plus vy y theta determinant. Okay, you now take this determinant value and this will be your Jacobian, right? So this is the chain rule or composition. Property number 3. If your u1 is suppose some function of x1, u2 is function of x1 and x2, and likewise your un is function of x1, x2 and xn, right? Then what will be your Jacobian in this case? This Jacobian will be here del u1 by del x1. Now then here it is 0 because with respect to x2 0, with respect to x3 0, so on 0. Now coming to this u2, del u2 by del x1, then here del u2 by del x2, and here with respect to x3 0, so on it is 0, right? If we go on continue, and it will be here del un by del x1, del un by del x2, del un by del x3, so on del un by del xn. So this is a triangular matrix here. Now this determinant is the product of the diagonal. Okay, so this will be here del u1 by del x1 into del u2 by del x2 and dot up to product of del un by del xn. So this will be your Jacobian. Okay, suppose you are asked to solve an example. Suppose y1 is 1 minus x1, y2 is x1 into 1 minus x2, and your y3 is x1 x2 into 1 minus x3. Okay, so is it not of this form? u1 is a function of x1, u2 is a function of x1 x2, and you are asked to find what is Jacobian here. Means you are asked to find del of y1, y2, y3 divided by del of x1, x2, x3. You may have the details of this, however the answer is this only, right? So that means what will be the Jacobian in this case? So you may have the details of this determinant, however if you evaluate this, it will be del y1 by del x1 into del y2 by del x2 into del y3 by del x3. And what is del y1 by del x1 is minus 1, and what is del y2 by del x2? If you differentiate it with respect to your x2, it is minus x1, and if you differentiate it with respect to your x3, it is minus x1, x2, is not it? So this is the product of this. So the answer will be here x1 square into x2, right? You may have your details of this work, del y1 by del x1, and it is 0 and 0, del y2 by del x1, del y2 by del x2, and it is here 0, and del y3 by del x1, del y3 by del x2, and del y3 by del x3. In that way find, or you directly find this. Okay, coming to one more example. Suppose you are given u is 2x minus 3y, b is 5x plus 4y, and you are asked to find the Jacobian uv, right? Jacobian uv is what you are asked to find. So your Jacobian uv, Jacobian is ux uy, vx vy, right? And ux, this partial derivative is 2, and uy is minus 3. Then similarly vx is 5, vy is here 4. You take the determinant. This is 8 plus 15 is here 23. So this is your Jacobian. So for short question point of view, you may be asked to find the Jacobian. One more example. Suppose you are given u is x plus 2y square minus z cube, v is here 2x square yz, and w is here 2z square minus xy, and you are asked to find what is Jacobian uv w. Means and what does it mean? It means del of uvw by del of xyz, right? If it is asked also find del xyz by del UVW, right? So what will be this? Now can you not find the coming to the first one? Also find this. Suppose I call it Z dash here. So now here Jacobian will be Ux, Uy, Uz, Vx, Vy, Vz, Wx, Wy, and Wz determinant, right? Just to evaluate it, it will be Ux is here 1, Uy. It is asked to find Jacobian at the point 1, -1 and 0, right? So Ux is 1. What is your Uy? Uy is 4y, right? 4y. So at -1 it is -4. 4y at the point 1, -1, 0. So is -4. And here Uz is -3z square at the point 1, -1, 0, 0. And similarly you find Vx, Vy, Vz at this point. It will be 0, 0 and -2. It will be 1, -1 and 0. If you evaluate this determinant, it will be at 6. Now if I ask what is your Z dash, right? No need to work out it. I can say it is my 1/6 because the property of the determinant. Okay. Coming to one more example. Suppose you are given one more question. It may be a long question. X is e to the power v sec u, y is e to the power v tan u. Okay, tan u. So you have to find Jacobian xy with respect to uv. So in this case, what is your j? J is xu, xv, yu and yv determinant. So what is xu? The determinant of this e to the power v silent. Derivative of sec u, it is sec u into tan u, right? Then here xv, sec u is silent. E to the power v is e to the power v sec u. Similarly here yu is e to the power v, tan u is here sec square u, the derivative of tan u. Then what is here yv is e to the power v tan v. If you multiply it, it is, if you multiply it this into this, okay, it is here u. If you simplify it, the multiplication e to the power 2v, it is here tan square u sec u minus e to the power 2v, here sec cube v. E to the power 2v taken common, sec u taken common, sec u taken common, it will be tan square u minus sec square u. So sec square u minus tan square u is 1, so it is -1. So minus e to the power 2v sec u. So this is your j here. Now what is for your z dash? Now to find z dash, okay, so what is your y by x? Y by x is e to the power v tan u by e to the power v sec u. E to the power v cancelled, so converting to sine and cos, it will give you sine u. And similarly here x square minus y square will be e to the power 2v sec square u minus tan square u. So it is e to the power 2v, right? Now, so this implies, you see, my u is my sine inverse y by x, and similarly here v will be, now taking log to both sides, it is 1/2 ln x square minus y square. Now you see, u is a function of xy and v is also a function of xy. Now you can find the Jacobian here. What will be z dash here, right? So z dash will be ux, uy, vx, vy, and you should solve it, okay? And it must be here minus of 1 by this, and if you simplify it, it will give you -1 divided by e to the power 2v sec u, okay? You should verify it all. So now therefore here j into z dash, is equal to here 1 is proved. Okay, so this is all about here Jacobian. Now this Jacobian will be used to evaluate the multiple integrals, where in complicated cases we have to evaluate the integral by bringing to other coordinate. Okay, where this Jacobian will play a key role. So if you think of its use, while you evaluate the multiple integral f xy dy dx, suppose you are evaluating with respect to over a region R. Now the moment I will change it to the polar coordinate, okay, so it will be my f r theta Jacobian dr d theta, right? So over the same region means while I put x is equal to r cos theta, y is equal to r sin theta, accordingly your Jacobian we have already determined is your r. So this integral will be integral f of r theta Jacobian is my r dr d theta. So here I am taking the limit of r here, and I am taking the limit of theta over here, right? I am taking here the limit of y over here, right? I am taking here the limit of x over here, right? So later on while we evaluate the multiple integral, we will see the use of the Jacobian. Now next coming to the Hessian matrix. Now coming to the Hessian matrix, suppose a function of two variables, we have f is suppose a function of x1 and x2. Now what is the Hessian matrix H, or I write it H x1 x2 here, right? Means I take the derivative of f with respect to x1 twice partially, then x1 x2, then x2 x1, then x2 x2, right? This determinant, right? And in short I can write it f11 f12 f21 f22, right? This. So here what do you mean by f x1 x1, or what do you mean by f11? This is my del square f by del x1 square. What is your f x1 x2? Means it is my f12 is my del square f by del x1 del x2, in that way, right? What is my f22? It is my f x2 x2, it is my del square f by del x2 square, right? In that way we should have. Similarly, what is here f21 is f x2 x1, it is del square f by del x2 del x1, right? So this is the Hessian matrix. Similarly, for a function of three variables, suppose you are given a function f is suppose x1 x2 x3. Likewise, what will be the Hessian matrix here? Here h x1 x2 x3, and it will be here f11 f12 f13 f21 f22 f23, right? And f31 f32 f33, right? This matrix, okay, this is the Hessian matrix. It is matrix, not the determinant, right? It is the Hessian matrix. Clear? Means similarly, if I ask you what is f11, means it is f x1 x1, means del square f by del x1 square. If I ask you what is f32, it is f x3 x2, it is del square f by del x3 del x2, in that way, okay, in that way. Now what is the major role of this Hessian matrix? This Hessian matrix will be used to study the maxima minima of the function, right? Now I should tell you the principal minors here. What are the principal minors of the Hessian matrix? Principal minors of the Hessian matrix. So now if we have f is here f of xy, so what is the Hessian matrix here? Here f xx, f xy, f yx, f yy, right? So now the Hessian matrix here will be the principal minor. Your D1 is the first principal minor, means you have the first order determinant, means fxx determinant. And D2 will be the determinant, this H itself, right? This is my Hessian matrix. This is the determinant of H itself, right? It is fxx, fxy, fyx, fyy, the determinant here. Now what will be this? This is fxx, fyy minus fxy into fyx, right? This determinant of this. Now under this continuity, we say fxy is the same as fyx. So I can say it is fxx, fyy in minus f square xy, right? If I denote it, my r, if I denote it my s, if I denote it my t, then I can write it rt minus s square, right? Now this will help you to find the maxima and minima for function of two variables. Now suppose you are given the function of three variables, right? Suppose you are given the function of three variables, is your f, x, y, z. Then function of three variables f, x and y, z. So what will be the Hessian matrix in this case? It is fxx, fxx, fxy and fxz. Then your fyx, fyy, fyz, and your fzx, fzy, fzz, right? Then what is the, this is my Hessian matrix. Now what are the principal minors here? Principal minors here. Your first order principal minor is this only. So what is your D1? D1 is that fxx itself, fxx. Now what is your D2? D2 will be second order principal minor, okay? Second order principal minor. Your D2 will be fxx, fyy, fyx, and this is fxy, this is fyy. So this is your determinant of this. Means keeping this diagonal fixed, okay? Keeping this diagonal fixed, we take the submatrix and we find the determinant. If I ask you what is D3 here, so D3 will be the total, keeping this diagonal fixed, fxx, fyy, fzz. We keep this diagonal fixed and we take the third order determinant, right? We take the third order determinant, means it is remaining fxy, fxz, and it is fyx, fyz, and it is remaining fzx, fzy. So in that way the principal minor, okay? So now this principal minor will later on lead you to find the maxima and minima of function of several variables. Coming to an example, suppose you are given a function f is suppose 2x1 x2 plus 2x2 x3 plus 2x1 x3, and you are asked to find the Hessian matrix. What is the Hessian matrix here? So Hessian matrix is f11, f12, f13, f21, f22, f23, f31, f32, f33. So what is f11? We differentiate f with respect to x1 twice. What is f1? What is f1? f1 is my 2x2. Now what is f11? Is here 0? Is not it? So what is f12? f12 means with respect to x2 again we differentiate f1, is here 2. What is here f13? f13 is 0, is not it? So similarly, what is here f2? f2 means here fx2. fx2 will be, it is 2x1 and it is plus 2x3. Now what is f21? f21 means with respect to again x1 we are differentiating, it is 2. What is f22? Right, it is here 0. With respect to x2 again we are differentiating, is here 0. And what is here f23? With respect to x3 we are differentiating it, so this will give you here 3 here, right? Similarly, what is here f3? f3 means here fx3. Now with respect to x3 we are differentiating it. So now it will give you 0 plus 2x2 plus 2x1. Now what is f31? Means again we are differentiating with respect to x1 is 0. What is f32? We are differentiating again with respect to x2 here. So it will give you 2. And what is here? F33. We are differentiating with respect to x3. So this will give you 0. So what is the Hessian matrix here? The Hessian matrix in this case will be f11, f12, f13, 0, 2, 0. And here f21, 22, 23. It is 2, 0, 3. And here f31, 32, 33 is 0, 2, 0. So this is the Hessian matrix here. f23, this has to 2, na? This has to 2. Okay, this has to get 2. So now the Hessian matrix. If I ask you what is your D1, your D1 will be 0 here. This is your D1. If I ask you what is your D2, D2 will be the determinant of this. D2 will be the determinant of 0 to 2, 0. This determinant value will be 0 minus 4, minus 4. And what is your D3? D3 is the determinant of this entire matrix 0, 2, 0, 2, 0, 2 and 0, 2, 0. Okay, we'll find this determinant. So this is all about the Hessian matrix. And this Hessian matrix, so where you find its use, we'll use it. Use of Hessian matrix. Hessian matrix. So we will use this Hessian matrix where to find the maxima and minima, right? Minima of function of several variable. Function of several variable. Function of several. So in this lecture we have discussed two important things. One is the Hessian matrix and other one is the Jacobian for function of several variables. As I have told you, this Hessian matrix will be useful to discuss the maxima and minima of the function, and subsequently it will lead you to convexity and concavity of the function, right, which will be one of the important aspect in your optimization in nonlinear programming problem. This idea will be used to find the convexity and concavity or the maximization and minimization problem, right? And here Jacobian will help you to find change the integral from one coordinate system to other coordinate system. If the integral in one coordinate system, xy system, is complicated, if we change it to polar system r and theta, it may be easy, right? So in our upcoming lecture we will discuss, we will discuss what? The maxima and minima, right? Maxima and minima for function of several variables. So function of several variables, 2 variables, 3 variables, in general n variables, which can be achieved by using the context of your Hessian matrix, right? So now if you find this lecture is useful and interesting to you, please subscribe to this channel so that it will boost my motivation to upload similar lectures for your benefits. At the same time, here many problems and examples will be solved, and which will help you to understand this chapter easily. So my request to you is that you should subscribe to this channel, also like this channel, and it will give me the motivations. Thank you for watching this lecture.